United States, and we will listen to an exciting conversation on low energy nuclear reactions. As you all know, clean energy, in particular fusion energy, is very crucial and on the top of our research agenda. In particular, at our institute, we have a program that is led by Professor Kılıç. Professor Kılıç was a collaborator of Professor David Nagel in the past, but nowadays he is a lead researcher at our institute on lattice-confined fusion. It's not exactly low energy nuclear reaction, but it is again another technology that addresses fusion energy. I will give a brief introduction of Professor David Nagel. Professor Nagel received his bachelor's degree in engineering science from University of Notre Dame, and then he had his master's and PhD degrees in materials engineering, both from University of Maryland, College Park. He has a very long career in low energy nuclear reactions. He started his career as an officer in the U.S. Navy, followed by a federal research center, a research scientist, and afterwards a federal research leader at the Naval Research Laboratory, which is a prestigious lab on material science research in the United States. He has a very long career as a teacher and researcher as well at the George Washington University, where he is currently a research academician, research professor. He taught numerous courses on MEMS and nanotechnologies, mentored a large number of both undergraduate and graduate master's and PhD students in these areas. Currently, he is leading low energy nuclear reactor reaction research at the George Washington University. In addition, he has a business. He has a role as a business developer also, not only as a researcher but as a business developer. In 2011, he founded NUCAT Energy LLC. This company provides consulting services and teaching services, instruction services on low energy nuclear reactions and other technical research areas as well. So we welcome you, Professor Nagel. It is going to be an exciting talk. Especially in our institute, we have a research program that is on low energy, very close to fusion energy. What we are doing currently on low energy nuclear reactions, which is lattice confined fusion. That's an area of research that we are concentrating in our Research Institute. The floor is yours, Professor Nagel.
Thank you very much, Orkun, for the invitation and the introduction. I haven't been to Turkey for a dozen years, and I'm very glad to be there virtually. Okay, it's a great pleasure.
Our pleasure. Next time, hopefully, in our future schools, hopefully we'll see you, on site.
Well, I would enjoy that greatly. But I worked with Turkish students at our university in recent years, and I'm very happy with that. So I would try and share my screen. Always an adventure. Let's see. I click on that. Let's see. You will. Okay. Can you see my screen?
Not exactly. We see a black screen right now.
Okay. So yeah, sorry.
Yeah, now we can see your screen now. Yes.
Okay. Now I have to figure out a way to get it to fill up my screen here. Now, can you see the
Yeah, it is
cursor
not
move
in full
around?
screen mode right now.
Okay, I just tried to put it in that,
Uh,
so it's working on it. So I can start while that comes up. As the title says, I'll be talking about the history, status, momentum. Around this field on both parts of it, the scientific understanding and also the uh, uh, commercialization. Now it says my internet connection is unstable. Can you see my screen now?
We can see, yes.
Yeah. Is it full screen or just part?
It's not full screen.
Okay. So I'll give it one more try here, and we may have to live with the partial screen here. Usually this works. I don't know why.
Okay.
No.
Now it is
Full screen.
Yes. Yeah.
Good. Okay. So thanks for your patience. So I have those 1, 2, 3, 4, 5 aspects of the field, and I'm going to start out by giving you a very, very brief summary of each one of them so that you know the answer right away. You don't have to wait for me to go through the entire talk in order to get to the bottom line. The history is very, very clear. The field started badly, which remains a problem, but that is fading into the past more and more as time goes on. The status of the field is very, very clear that it is possible to produce nuclear reactions at low energies, and they are very promising. Okay, the characteristics from the experiments that have been done in the last 35 years are both promising and exciting. So there's more momentum now, much, much better than it was even a few years ago. But the funding is still too low, and I'll complain about that later on in the talk. The possibilities are major applications and impacts. When I talk about them, sometimes people accuse me of being overexcited. But I'll happily suffer that criticism because I think that we do have some really exciting possibilities. And the two big challenges are crystal clear. Understanding how it is possible to produce nuclear reactions without large accelerators or high temperatures. So that's the most urgent thing from a science viewpoint. And then taking advantage of the empirical characteristics that have been found in lots of experiments in lots of countries for lots of years. Okay, so that's also very, very interesting. So this presentation is about a potential new source of clean energy that has the following characteristics. Because it's possible to get energy gains, the energy could be cheap. I'll talk more about that as we go on. There's a high energy density because we're dealing with condensed matters, not dilute plasmas. So we may have widely distributed, pardon me, and maybe even mobile sources. Okay, that's driving the commercialization very strongly. And happily, it's safe. There's negligible dangerous radiation, don't need a lot of shielding, and no radioactive waste to speak of, and no greenhouse gases because it's nuclear. So I make a very bold statement at the bottom saying this new source could do for energy what cell phones did for communications. And I could belabor that, but I'll just leave it at that and move on to the next slide here. So this is an outline. Excuse me. It's early here. So above the first dotted line is the introduction. I talk about some things that most of you probably know, but I am going to go over them briefly to set the context to talk about LENR in the main part of the talk as indicated here. And at the end, I've got a couple of view graphs on what we're doing on using modern artificial intelligence to assist with our research on LENR, both planning programs and experiments, as well as understanding what we're seeing. So I go through this. My understanding is we'll have the Q&A at the end. I will happily entertain questions, but I guess we can wait till the end for those. So I'll tell you something you know already. We get our energy, which along with matter and information is an extremely fundamental part of our lives. We get it from movement of masses, air, wind, of course, and then water, whether it's streams, dams, waves, or tides. We also get energy from overhead and underfoot, the sun and the earth. And then, of course, we get much of our energy from reactions, chemical reactions, mostly fossil fuels. And in this talk, we're focusing on nuclear reactions. And that's set in the context of fission and fusion, as well as the subject of this talk. So I'm going to step through these and talk about things that are relatively well known. I hope you won't be bothered by that. It won't take too long, and then we'll get on to LANR. So chemical energies have useful power densities. It's possible to drive a car that weighs a lot, a ton or something, up a steep hill with a very small amount of gasoline. Their cars are well engineered and widely used. It's well known. But when you back off and look at the fossil fuels, be it coal or oil or gas, there are a couple of problems. Even though the power densities are useful, they're not that high, and you need massive amounts of coal, oil, or gas in order to run our societies. Oh, and then there's this problem of global warming that has come along in recent decades, which is very vexing, especially sea level rise and everything that's associated with that. So chemical reactions, glad we have them. They make the world go round on one hand, but hopefully we can do better than that. Now, turning to nuclear reactions, as you know, some of the binding energy of the protons and neutrons in the nucleus can be released and used, and there are two main ways to do that. You can split heavy nuclei of uranium or plutonium when they're impacted by a neutron, the fission, of course, or you can jam together isotopes of hydrogen, fuse them when they hit each other at high kinetic energies, high enough in ordinary fusion to overcome the mutual repulsion of the positive nuclei. Now, I put in the bottom here the three isotopes of hydrogen. We'll be talking about the first two a lot. And again, most of you probably know this, but you have protium, a single proton, heavy hydrogen or deuterium, which has an additional neutron, and then the radioactive isotope tritium, which has a couple of additional neutrons. So you're going to hear a lot about deuterium during this presentation. Now, how is it that you can get nuclear energy from both ends of the periodic table? Well, that's explained by this plot. Horizontally, we have the size of the nucleus, number of nucleons in the nucleus, number of protons, and the number of neutrons. And then vertically, we have the average binding energy per nucleon measured in millions of electron volts. So for fission, you split a heavy isotope to get lighter isotopes that are more tightly bound. Some energy is released, and you have a smaller energy release per nucleon, but lots of nucleons. Okay, so you can get a lot of energy out of fission reactors. And then at the low end of the periodic table, you put together the isotopes of hydrogen, and you get a lot of change per nucleon, but only a few nucleons. And then, of course, you have the famous equation from Einstein that governs the energy release due to the mass change. Now, this is a cartoon you're familiar with. In fission, a neutron comes into a heavy nucleus, it splits into two lighter nuclei and puts out additional neutrons, which can go on to create additional fissions in a chain reaction. The good news is it's clean, no greenhouse gases, but the facilities are very large And after the reactor runs, we're left with very long-lived radioactive waste. The concern about safety is real. There have been some, famous accidents, Chernobyl and Fukushima and all, but basically fission reactors are generally safe. There are, I think, about 450 power reactors in the world, another couple hundred research reactors, and then you've got reactors in ships and submarines and all. So it can be very good. It's undergoing a resurgence right now in some countries. Now, turning from fission to hot fusion, the idea here is to cook up the isotopes of hydrogen shown on the left, deuterium and tritium, which interact with each other in order to produce helium and an energetic neutron that has to be slowed down in order to capture its kinetic energy, turn it into thermal energy. The drawing on the right is a cross-sectional view of the ITER, International Thermonuclear Experimental Reactor, being built in the south of France at a, excuse me, very large cost, a very long time, behind budget, behind schedule. But it's seeking to show that you can get a gain of 10, that is 10 times more nuclear energy out than you put in electrical and other forms of energy. And that would be very nice, okay? But the problem is the plasma has a temperature of 100 million degrees, and it's immense. On the left are the floors in the building that holds the ITER reactor. 1, 2, 3, 4, 5. So if they're each roughly 3 meters, that's what, 15 meters. It's big and expensive. And if it works, gives a gain of 10 as hoped, then you'll have to build another experimental reactor called demo, and then maybe on a scale of a few decades, you'd have hot fusion power on the grid. I've worked in that area before. It's possible that it will turn out to be extremely important. Maybe a century from now, most of the world will be powered by hot fusion, but maybe not. We will see. Okay. Now, while ITER grinds forward, several large, I misspoke, sorry, a large number of smaller companies has sprung up. Some of the names are listed here, not all of them, it turns out. And they have substantial funding. Some of them have most of $1 billion by themselves, okay? So they're saying that we don't have to wait for ITER to work and then the demo and the large scale international program. We're going to do it on a scale of a few years, and they've gotten a lot of money from investors. So from my perspective, as we move along in the LENR field, we have the opportunity, in fact, the need to watch what's unfolding in the hot fusion world in order to see how they're doing. It's in some people's view a race, and it's not unfair to characterize it that way. So we'll see how it turns out in the end. Now, leaving the background and turning to LENR, this is a photograph of Fleischmann on the left and Pons on the right during their infamous press conference on the 23rd of March in 1989. Fleischmann, a British fellow, and Pons, a United States scientist, very, very interesting people. They had this press conference, and it was really big news, immediate news, okay? And in fact, a few weeks after their announcement that they could produce nuclear reactions in a tabletop experiment, the 3 major news magazines in the United States had cover stories on what was then called cold fusion, which we now call LENR. Fusion or illusion, miracle or mistake. It was a really, really interesting time. It was pre-internet. I mean, the internet existed, but wasn't widely used at that time. So we were using faxes. We would get a fax of a fax of a fax, could barely read it. It was a very memorable, very, very interesting time. And I was glad to be involved in it from the beginning. So when it comes to chemical reactions, also nuclear reactions, you have this well-known situation where you put reactants and some initiation or activation energy into a reactor of sorts, and you get out products and energy release. And the cartoon on the lower left shows the reactants of the products on an energy scale, and the difference between their energies, the energy release, what you're looking for. But there's this barrier, this initiation energy, which in the case of hot fusion is the Coulomb repulsion between the nuclei. But the big deal here, and what made people incredulous when this was first announced, is the difference in energy scales between the chemical scale, like a electron volt or so, and the nuclear scale of millions of electron volts. How is it that you could get over the normally large activation area on a scale of MeV, many keV, MeV, in order to realize nuclear energy releases by using only chemical energies? Okay, so as soon as Fleischmann and Pons made their announcement, there was a lot of controversy. And what I've listed here is the things that came up then and subsequently about this field and why it's such a problem. Okay, now if we had a lot of time, I would go through these. You're in luck. I'm not going to go through them. They're part of the presentation that you have. You can look at them as you will. I'd be happy to discuss any of them, of course. But the field got off to a bad start and was declared by some, even in the year of the announcement, 1989, that the field was dead, over. I got a letter from a colleague in the fall of 1989 asserting that my career was dead. I was essentially done as a scientist because of my interest in LENR. It turns out not to be the case. Happily, we're down the road 35 years later, and I'm still able to work on this. So I'll go by this. Okay, so to talk more about the status of LENR, as I said already, it's real. There have been thousands of experiments in many labs in about a dozen countries, oddly, mostly in the Northern Hemisphere, and in Europe, Asia, as well as America. And there's a strong database, as I'll note later when we get to the AI part, over 5,000 papers and reports. There's a lot of information available. That's the good news. The bad news, still not understood. If we did understand LENR and could explain it to physicists and chemists and others in the scientific community, it would be better accepted than it is now. Okay, it has been chronically underfunded, as I will note more later. The hot fusion people have billions of dollars. We have millions of dollars. So for every $1,000 they have, we have $1. And are trying to understand and commercialize the field on the basis of that kind of funding. So again, a remarkable scientific problem and a promising new clean energy source. So if you're an engineer, this is worth paying attention to, because you want to build reactors that work for usefully long times. If you're a scientist, you want to understand it, whatever the practical outcome. Okay, so I say I have long counted myself as being very fortunate to work in a field that has these two phases. Excuse me. Now, the generic LENR experiment is some chamber, the experiment itself, into which active materials go, and then you put in the energy in the reactants, so you get out the additional energy and the products. It looks very, very simple, but the only problems are the active materials, and the input, and quantitatively assessing the output. It looks small. It is small. It looks simple, but it's still very, very challenging. We have a very well-equipped and active LENR laboratory at our university. I'd be happy to show it to you if you get to the Washington area. But anyway, it's a field that is deceptive in a sense. It's much richer in its intellectual and experimental and other aspects than it appears to be. So the fundamental thing that has to be done is to put protons and deuterons together with materials. That's the mixing part. And then make them move relative to each other so they can interact and react. That's the motion part. And the field started with Fleischmann and Pons taking small pieces of palladium, which soaks up hydrogen or deuterium to a high degree, and loading them with deuterons, okay? They used electrochemical means. Other people use hot gas means. Plasma means look very, very promising. So that loading approach is one. But you can also simultaneously deposit palladium and deuterium and see evidence of nuclear reactions, or you can dry mix chemicals and then run a current through them. Okay, so very important work that has been done by Schwartz in the northeast of the United States. The motions come from diffusion, come from electromigration, which is the driving of the movement of deuterons and materials by an electrical current, and then atomic vibrations can play a role. It's been well established by now that high temperatures favor the production of LNR energy. And when we're talking high, we're not talking about millions of degrees like hot fusion. We're talking about hundreds of degrees centigrade. Essentially the kinds of temperatures you find in a furnace burning fossil fuels. So the experimental approaches involve materials, methods, and measurements. On the left part here, you have what goes in, the materials, and in the center, the methods, electrochemical, gas, plasma. I also included beams in the bottom because of some very important science that's being done with beams, even though it's unlikely that there will be any beam-based practical generators. So most of the work has been done with palladium and its alloys, deuterium, or nickel and its alloys involving protons. And then the dominant measurements have been done of heat, so-called excess heat, and nuclear products, what remains after the reaction happens. So as noted here, the two most common combinations are palladium with deuterium and nickel with hydrogen. Excess heat is the term that's applied to the thermal energy that comes out of an experiment in excess of or on top of the input electrical energy. It's measured with calorimeters, gives the thermal power out as a function of time. You can integrate that to get the energy out. And a lot of people are put off by calorimetry, and they're very, very commonly used. If you go to the grocery store and you pick up a package that tells you how many calories are in that food, and that's a measured value. They're widely used. They're conceptually fairly simple and can be understood. We have designed, built, calibrated, and used calorimeters where we can get the calibration by 2 or 3 different methods. We can calculate the calibration constant, and it agrees with the measurements. So anyway, it's no mystery. As I say, some physicists who've not dealt with calorimeters are somewhat put off by them, but I can assure you from my own experience as a physicist who didn't know anything about calorimeters in 1989 that you can master that tool. Okay, so what I will have a few data graphs in here and in the following, which will be a little complex, but this is a technical talk. You can handle it. I will explain it, and if I'm not clear at the end, you can ask questions about them. So on the top of this, it shows 2 deuterons coming together in both ordinary hot or beam fusion, and then in cold or LNR. And in hot fusion, you usually get a 50-50 split between the 2 branches shown in the top there, getting out a neutron and a helium-3 on one hand, or a proton and a triton on the other hand, with a very small fraction, like 1 in 10 million, resulting in a helium atom and a gamma ray. Now, by contrast, in the LNR area, you get very few neutrons. You get some tritons and charged particle emission, proton emission, And you dominantly get helium, but the energy does not come out as a gamma ray. Okay, comes out as heat energy. So you have to explain to understand LENR how it is that the reaction product is coupled into the lattice as it is. Now, on the bottom is a graph from Ed Storms, a compilation, his reading of many papers. The horizontal axis is a log of the ratio of the number of helium atoms that are produced to the energy that is produced. Okay, so the people who did the papers that resulted in the data that's shown in this graph did two measurements. They measured the helium production and they measured the heat production, and then they ratioed them to get the value here, very near to what you would get from a DD reaction in a hot fusion case, about around 24 million electron volts per reaction. So the vertical axis is just the paper count, the number of papers. So we have a very good correlation between two totally independent measurements in the same experiments. Energy, heat, say from integrating the power that's measured with a calorimeter on one hand, and then chemical reactions or mass spectrometry commonly to get the number of helium atoms. So this is something that a lot of people in the broader scientific community don't appreciate, that people have done these measurements, calibrated the instrumentation, formed the ratios, and gotten the data that's shown in this graph here. Very, very, very important. Now, the next graph is the worst graph that I'll show in terms of complexity, but it's very, very important. And I'll take a few moments to explain it. On the left is data from measurements after LENR reactions, and on the right is data from beam experiments, low energy beam experiments. So in both cases, you have the periodic table left to right. On the left, it's in terms of mass number. On the right, it's in terms of atomic number, but it's the periodic table. So what you have on the left part of this graphic on the top is data that was taken in the middle of the U.S. In the state of Illinois near Chicago, of the production of elements in a particular LENR experiment. And it scatters widely, but it seems to be peaked. There's some regions, in this case of the mass distribution, that show where the elements show up more than they do in others. Now, setting that aside, looking at the lower left hand, we have a similar plot from an experiment in Hokkaido by Mizuno, where he also measured the production rate. And interestingly, it's scattered, but it shows some peaks. And the peaks measured in Illinois, in the US, and in Hokkaido in Japan align with each other. Well, isn't that interesting? Okay, so setting that aside, looking at the right-hand part, you have two plots, one made by Chersky in Poland on the top and another by Kasagi in Japan. And again, it's a function of atomic number. And it's a quantity called the screening energy. And it comes out of low energy beam experiments. And it basically is a measure of how much more deuteron reactions you get, how much of an increased rate compared to what would be expected by extrapolating data from higher beam energies. And you look at it and you say, there seem to be peaks. Oh, and they line up together with each other in the two compilations. That's not surprising because both Chersky and Kasagi made their plots based on the literature, the same literature. But wait a second. Do the peaks in the screening data from the beam experiments line up with the peaks in the transmutation data from the LENR experiments on the left? And the answer is yes. There are 5 peaks in both cases, and they line up with each other. And that's just astounding. Okay, so that's one of the major problems that is remaining to be explained here. It speaks to the to what's actually happening in the LENR reactions, be they caused by beam experiments or by the electrochemical experiments, which generated the data on the left. It's a very to me, a vexing and exciting problem. And Lee from Tsinghua University in Beijing has a paper that might be widely accepted as an explanation of this data. It's good fun. So now turning to the practical side of this, excuse me, we have a so-called Ragone plot. Horizontally, it's energy density, measured in watt hours per kilogram, and vertically it's power density, watts per kilogram. And ordinary current and projected energy and sources and storage devices are in that shaded area in the lower left-hand part. Two of them are shown explicitly: lead-acid batteries and petrol. And then you have out on the upper right-hand corner of this graph, three data from LANR experiments, one reported by the Italian Preparati in 1996, some data from a guy named Rossi, Italian guy, also the ECAT, and then a Nanor, the name of the device that Schwartz in the US has produced. And you look at them, you say, oh, that data is widely scattered. Excuse me. You look at the axes here. These are this is a logarithmic plot in both directions. So those three data points for LANR experiments are widely distributed. But you look at just somewhere where they are relative to the petrol. They're 1,000,000 times higher in energy density and 1,000 times higher in power density. And since this graph was made up, another point has been added out in that oval. So anyway, it's based on even this limited data, but encouraging data that we think we might have very high power densities and could produce a nuclear power source in your home. Okay, and that's what we're working towards. Okay, so this is getting a little ahead of myself, but the hot fusion people are even in the smaller experiments dealing with very large and relatively expensive facilities that will not be distributed in homes. They're going to be central power plants and rely on the grid for the delivery of energy. And by contrast, we in the LANR field are hoping to make distributed commercial power generators, energy generators that are small enough to be used locally. And that hope is based on the high power and energy densities. Now, if you want more information on LANR, you can look at these sources. Jonah Messenger's article is very good. And then there's a website that has a lot of information. Okay, so where are we? Momentum. So LANR research has been done, I say, in about a dozen countries for a long time. Japan has had major programs for many years, largely but not exclusively based on hot gas experiments. You cook up a gas of hydrogen or deuterium. The molecules run into each other. They're disassociated, and then they're ionized, and the hydrogen nuclei, be they protons or deuterons, enter the materials for reactions. Now, Google funded an LANR program dominantly in the US from 2015 to 19. The EU started two major programs, 2021, you see here. There's been sporadic investment, a lot of it private investment, small scale though, in the US. And finally, the US government started an LANR program almost 2 years ago. So LANR is seen there's this incredible database of information, and the only way to make it go away and to show that LANR, there's nothing to LANR, is to find ways to discount the program, saying that these people didn't do the right calibrations, they didn't do it, or they lied, they just made up and published the data, and that's just simply not the case. Now, some of you might be looking at this graph saying, why are three of these lines in red? And the answer is because each of those programs, the Google program, the EU program, and finally the US program, are in the order of $10 million. Okay, substantial funding. Excuse me. Very good work being done by very capable people in those programs. So I'm belaboring this now. The possibilities of LENR are that you can get gains. You can put in 1 unit of energy and get many units of energy. So there's somebody listening to this say, wonder what the highest gain is. Well, the highest reported gain, which has not been reported or independently verified, but nevertheless came from a competent and, in my mind, trustworthy scientist, Mizuno in Japan, is 800, 800, compared with a gain of 10 that is being sought in the ITER experiment now with all that money and all that time. There are other experiments, LENR experiments with smaller gains, you know, a few. But wait a second, if you had a gain of, pick a number, 5, 8, something like that, that could reduce your energy bill by a factor approaching that. Okay. So as I've said, high energy densities enable small systems, and we are free of dangerous radiation, significant radioactive waste, and greenhouse gases. So I say the bottom line is at the bottom here, the development of LENR generators could lead to having multi-kilowatt nuclear systems in homes. A very exciting prospect. Okay, now let's see. Here. So you might say, hey, this Nagel guy, he's a salesman. He's trying to sell me on LENR. Well, there got to be problems. And of course there are problems. I mentioned the 2 big problems already, understanding and commercialization. But within commercialization, there are 2 other very large and important problems. One is scaling the power up from watts to kilowatts. Okay. And the other is the reliability of materials. You know, hey, imagine you go down to the store, you buy an LENR generator, you get it installed in your home, and it works 2 weeks or 2 months. You know, it's got to work for years. Okay, so reliability is a challenge. The good news is that there are many materials that have been shown to be LENR reactive. The bad news is that if you run their temperature up to hundreds of degrees centigrade during operation, diffusion, it's unstoppable and can degrade the materials. Now, there was an experiment in Japan by Arata where he reportedly produced power on the scale of 10 watts or so for almost a year. Okay, so there is encouraging data, but nobody has made yet a kilowatt generator that will run for usefully long times. Now, the theory of LENR comes up all the time. Of course, we want understanding. You know, in some fields of science, understanding was available immediately. If you look back at the paper published by Mossbauer, he had the experiment and the theory in the original paper. Okay. By contrast, if you look at superconductivity, discovered in 1911, not understood till the 1950s, there's a gap of decades between discovery and understanding. So anyway, there are about 3 dozen concepts for how LENR works. Only a few of them have been written out as equations and evaluated to produce numbers for comparison with measured results. It's one of the shortcomings of LENR is that a lot of the theoretical work has been incomplete. At the bottom is a title, an abstract of a review paper that I wrote with a couple of Hungarians who did some very sophisticated theoretical work. It may turn out to be wrong, but it was worth looking at, well-founded in ordinary physics, and we'll see how that works out. Okay, so I could go on and on about theory, but I'll restrain myself by showing just one other thread of research that's very important. It originated in Czerski's lab in Poland. where your Professor Gillich worked for a long time. It has to do with screening and resonant enhancements of the DD reaction. Here the deuteriums are designated both as H2 and as D, and in this particular reaction going to a proton and helium-3. So that work, which you see the first paper is from 2016. It's been underway for a long time. High quality experimental and theoretical work. And then more recently, you see 2022, Chursky published a paper that may have the answer in it, the answer to how it is that LENR works. He has fusion reaction cross sections from beam energies at kilovolts down to the energy equivalent of room temperature, about a few percent of an EV, and very exciting. And the steps that are necessary is for more people within the LENR community, and especially people outside of the community, to look at this work and to scrutinize and criticize it thoroughly, so that if it, as I expect, withstands criticism, it will count as one of the most promising explanations of how it is that LENR works. So I salute this work. I'd like to talk more about it now, but let me go on, because I'd like to stay on time here. Okay, so this is a scientific field. We have a series of conferences, the International Conferences on Cold Fusion. We've retained that cold fusion moniker, even though LENR is the dominant name of the field now. 25th such conference was in Poland in 2023. The next one will be in Japan next spring. I've been to all 25 of these, and find them exciting. Some people have accused folks in our field of being nuts, being kooks. And I tell them, if you come to one of our conferences and listen to a person standing up saying what they did and what they found and responding to criticism, you might think you're at a scientific conference. I mean, this is good science, whatever accusations have been leveled against us. We have a scientific society, the International Society for Condensed Matter Nuclear Science. Excuse me. We have a referee journal, electronic journal, a good journal. So anyway, we have a strong scientific field. But wait, what about commercialization? Yes, there are companies. You have these 6 companies: Bruin in California, Clean Planet in Japan, ENG8 in Portugal. They went there a year ago, and they ran an experiment that claimed to produce a gain of 3 from 0.4 to 1.2 kilowatts. Okay, I say claimed. We couldn't calibrate their instrumentation or their program, but there's no reason to think that they were lying to us. ECAT in the US, Mizuno Technologies in Thailand, and most recently High LENR in India. So you have these companies in various states of development, and it's the potentially new industrial association. I misspoke. Industry on LENR is coming forward. So 2 of us formed the LENRIA, the Low Energy Nuclear Reaction Industrial Association, about 10 years ago, in anticipation of the emergence of a new industry. Okay. If you look at the whole LENR ecosystem, consists of government agencies, other organizations, core organizations in the lower left, information and businesses, and so forth. So there's a lot going on. I have colleagues, professional friends all over the world. I'm in constant contact with them, and I find it very, very interesting on all levels, from a quantum mechanical wave function up to sociology. It's exciting. So to finish up, I have 2 graphics on a program that we have with the New York University that is aimed at mining the LENR literature. And the fundamental situation is that there are, I think I said, over 5,000 papers and reports in this field. I've been in it. I've heard most of the presentations, read most of the papers, but I can't remember everything. Okay, so we have a suite of sophisticated old and new AI tools that we're using to mine the existing literature on LENR for actionable insights that we could otherwise not see. Okay. And it's working out very well. So we have the LENR literature in the computer in a form that can be swallowed by AI programs, mined, if you will. And we're working towards making that widely available. We're also developing and deploying new and modified AI tools to support and accelerate both current and planned LENR research commercialization. This is a very interesting and exciting program. And when it's widely available, let me go back. I forgot to mention, we have lenrdashboard.com. If you go to that, you'll find our capabilities on display there. Okay. It turns out yesterday that was down, but it may be back up by now. Anyway, it's there for you to try when you get a chance. So when we're done on a scale of a year or two, we will leave behind web-based tools, so scientists who are working on LENR can use the tools to rapidly and creatively search and mine the existing literature. Writers who want to learn about LENR can use it. There are lots of bad articles written by scientific writers on LENR. Hopefully that'll change. If you're a newcomer to the field, you can use these tools to help easing into it. And students, who are attracted by the promise of LENR have a practical way to learn about it. So I hope I've given you an overview. You can capture what's going on experimentally, scientifically, as far as information goes now. If you watch a soccer match 3 or 4 hours later, you'll know what the answer is. This is going to take decades to play out. You have to be patient. Okay. I'm 86 years old now, so I won't live long enough to be able to go to the store and buy a reactor based on LENR, even though I'm working on that. But I'm hopefully going to live long enough to achieve the understanding with my colleagues of what's going on. So let me get out of that mode and close this screen and try and respond to any questions you might have.
Thank you, Professor Nagel, for this very comprehensive introduction to LENR. And we wish you a long and healthy life so that you contribute more.
Well, thank you.
And thank you for all your contributions and this introduction. Now, you cite as an evidence, of the existence of a nuclear reaction. Basically, 3, aspects, experimental observations. One is the excess heat. The other one is observation of helium and sometimes other nuclear byproducts, but with no gamma radiation. And the third is the transmutation. And they are definitely, very strong evidence for the existence of a nuclear reaction. But how repeatable are they? Is it easy to validate these results, or if it is not easy, what do you think are some of the obstacles, experimental maybe, or physical obstacles in repeating these experiments?
Yeah, the short response is it's not easy, and the main problem is materials. Okay, so this strikes close to home for me because my academic background is in materials, as you mentioned at the introduction. The aspect of materials, 2 main aspects: composition and structure. What atoms are there and how are they arranged in space? And of course, when you go to structure, you get into the basic lattice structure, all the defects, point defects, line defects, surface defects, 3-dimensional defects, all kinds of complexities, normal material complexities. And it's clear that you need the proper combination of both composition and structure. I mean, there have been experiments by very, very good people in the field where they'll use palladium and get positive results, get excess heat, get transmutation products, and they'll run out of the material, that they got at some time from some company like Johnson Matthey in the UK. So they'll go to the stock room and get another spool of the nominally identical material, and it doesn't work. Okay, or a material won't work and then it will work, or it will work and then it won't work. There are very, very, very frustrating materials aspects of this, and that's why I tried to emphasize the materials reliability.
So there's something missing in the theoretical framework, it seems, right? The theoretical explanation of the entire reaction, nuclear reaction that's taking place. So that's an area that needs to be improved. But how do you explain the non-existence, of the gamma radiation? You observe some byproducts, even transmutation of certain elements, but how do you explain non-existence of the gamma radiation?
Yeah, so I go back to the materials for just a moment. Storms has an idea that the reactions actually occur in gaps in materials. Okay, and he has a pretty good argument for that. Okay, but but he still cannot explain, on a very fundamental basis why the reactions occur. You might say where they occur, what's necessary, but not what's sufficient. So anyway, that you said it well. There's still major concerns there. So turning to the absence of gamma radiation, it's a well-founded observation. There are some gamma rays in some experiments, but they're nothing consistent with the rate of reactions as indicated by either the heat or the transmutations, the chemical reactions afterwards. And we don't have an explanation of it. I mean, and that doesn't mean that there isn't an explanation. Lee, the fellow I referred to from Beijing, has a theoretical paper that, if he's correct, will explain the lack of gamma rays, that the reaction products are not created in excited states, in contrast to what happens in beam experiments and in high temperature plasma experiments. But his paper, which is relatively new, I think it was a year ago or so they put it out, has not been, I think, even widely read, let alone widely accepted. He may have the key insight, a resonance-based idea that he's worked out on one hand, but it could be that when his paper gets adequate scrutiny, that it doesn't withstand that scrutiny. I expect it will, as a comment, but so one person and his colleagues, Lee, Xingzheng Li, has an explanation why LENR can occur without significant gamma emission.
Okay. So the next idea that occurred to me, during your presentation, as you gave the evidence, scientific evidence on the effect of the Coulomb, interaction, the effect of electron shielding, on the rate of nuclear reactions. Professor Kılıç, in our site, is pursuing nuclear reactions, lattice-based, lattice-confined fusion reactions, and we have observed the same effect, the effect of electron shielding, and he is looking into different means of improving, this effect, so that the fusion rate can be increased, to much higher levels. In your application, what do you think could be done to improve this electron shielding effect?
That's a tough equation for me because I'm not a specialist in it. I've read the papers. I've written a summary of it that's going to be part of a book I'm writing. But I am excited by the prospect of a mesh having an influence on the reaction rate. Professor Kilic talked about that in Poland, as I recall. I'm hoping to see him in Japan next year to learn more about it. A very fascinating possibility, because it's an interaction of things on a small but still macroscopic scale on one hand, and then on a microscopic, an atomic and nuclear scale on the other hand. So I don't have an answer to how to improve that. What I'm doing scientifically right now is running LENR electrochemical experiments with various means, doing co-deposition experiments, and commercially I'm seeking a patent on an approach that I think has promise as a commercial generator, and I've got money lined up to pursue it if I get the patent. But so I'm hoping to take what is known and build a practical generator, and then improve it, increase the reaction rate, increase the reliability, controllability, durability, all the things that we want for a generator, rather than being able to answer your tough question about now how to
Sorry,
improve.
for addressing all these tough questions, but these questions also occupy our mind,
Of
especially
course.
Professor
No.
Kilic, he is the lead researcher on lattice confined fusion in our institute. He is also looking into different means, of improving this electron shielding effect, to increase the tunneling rate, and also as a result, to increase the fusion rate. Professor Kilic, do you have any to say on this?
First of all, I would like to many thanks to Dave for this wonderful presentation. The concept of cold fusion has been a controversial topic for many years. Moreover, many scientists, including myself, approached the concept of cold fusion with skepticism. To enable and success neutron-neutron fusion reactions at very low energies, we actually need two key concepts. First, we require materials with high screening energy to reduce the Coulomb barrier at low energies. And maybe this is the answer for why we couldn't repeat some experiments about cold fusion. The main factor is the concept of zero plus subthreshold resonance, for which I developed calculations and a new formulation during my PhD thesis. The zero plus resonance is, in fact, a material-dependent resonance structure. And since this resonance is very narrow, very thin, and its position varies depending on the material. So capturing this resonance is indeed a significant challenge. So this is also connected with compound structure of helium-4. So first of all, we should determine the position of the helium-4, and also this is strongly dependent on the position of the material. The position of resonance strongly depends on the material, and this resonance could be developed or extracted from nuclear physics experiments. And here, once again, I would like to say many thanks to Dave. And I have also one question here. My question here is this: could there be other nuclear physical effect that might trigger this neutron-deuteron reactions at low energies? That was my question. So we know, okay, so we explained, we tried to understand zero plus resonance and screening effect, and there could be another nuclear physics effect at low energies. What do you think about this effect, David?
I'm dependent on the literature to answer that. So to respond to that, I don't have an answer. Okay.
I see.
So there are possibly other effects that have not been examined yet. But my sense of it is that given that we've been working on this for 35 years, there have been lots of ideas. Some of them are very difficult, out of hand. They can be criticized easily. But if I understand you correctly, Ali, you're asking if I have thought of some other effect that could be the explanation, and if I understand you, and I think my answer is very clear. No, I'm not a theoretician. And I say I watch the theoretical literature. There are papers by competent physicists, Hagelstein at MIT, Muhlenberg, many others, the deep orbits, deeply bound levels. These things are in play. They require examination, discussion, understanding. They're getting some of that on the internet, separate from ordinary publications. But I don't have anything to add to that, sorry to say.
Okay, but do you agree about zero plus resonance structure, because it is strongly material dependence resonance structure, and then very narrow, and it shifted belonging to materials.
Yeah,
so maybe this is the answer for a reputation,
yeah, I'm extremely interested in that resonance and the interaction between that and screening, and the materials dependence. The work that you've done, the work that globally has been done in Chersky's group and Kasagi's group and elsewhere, says, look at this, it's important, and if you can tune the materials, choose materials in a way that influences screening, in a way that therefore influences the interaction between the screening and the resonance level that you mentioned, and increase the reaction rate based on that could be extremely important. Whether or not it'll turn out to be practically important as well as intellectually important is an open question right now, of course, but it's a very, very good program.
Okay.
TÜBİTAK, as you know, is also, we conduct research, but at the same time, we are a funding agency. So I wonder, how do the funding agencies like ARPA and other maybe DOE labs view, this technology in terms of its funding potential? What is the tendency, to fund this research in the US?
Yeah, there historically has been work at a number of labs, Los Alamos, Livermore, the Naval Research Lab, other big labs, that was based on individual interest. So we did things at the Naval Research Lab because it was a big lab. Excuse me. We had enough money, we could do some work on it. And that sort of decayed away over the years. And then happily, in a few years ago, the so-called ARPA-E, part of the Department of Energy, started to get an interest. They had a workshop. Pardon me. They were able to get $10 million for a program that runs a few years. They funded, I think, 8 different organizations. They're good people. So that program is grinding along now. A couple of years down the road, I expect good things to come out of it scientifically. Whether or not anything practical will come out of it is to be determined. But if it does result, as I hope and expect, in some good data on not only the reality but the characteristics of LENR, then they'll probably follow it with additional funding. The Department of Energy is immense. For them to increase their funding from the $10 million level to, say, tens of millions, even 100 million, in order to get a dedicated program on what's needed, that is the materials aspects, as well as just a lot of parametric experiments, is very, very possible. Okay, I'm an optimist.
Yeah, I mean, as compared to magnetically confined fusion, the levels of support is very minimal, So, but I hope it increases because it's a very promising technology, as far as we can see. Do you continue doing any experimental research at the university?
Yeah, so our laboratory has 3 electrochemically based calorimetry experiments running right now. Okay, with the ability to put a current along the cathode wire to promote electromigration, to promote reaction rates. Okay, so we're doing those experiments, and we're doing related experiments on co-deposition, studying the materials that result, trying to measure the sound that's emitted, trying to measure the infrared that's emitted, radio frequencies that are emitted based on papers that have been published in our field. So we're very active right now. We're underfunded. We don't have enough people, but we do what we can, and it's exciting. It's fun. People have said to me many.
Our experimental research nowadays, it's more focused on experimenting the fusion, cross sections, of different materials, different material systems. So, we hope to observe, some of the resonances, that Professor Kılıç, has mentioned, experimentally, as well.
Yeah, I hope that you have continued success. There's been a lot of good that's come out of that line of work so far. I'm glad it's being continued where you are, and I say I'm excited about the possibilities.
I don't see any questions on the YouTube channel. It's not easy for me to access the YouTube channel while I'm on the Zoom screen. But I have not been told, that there is an additional question on the channel. So in case there are no further questions, it's been a pleasure, to meet you and listen to you. We have learned a lot, from your broad description of the low energy nuclear reaction research. And we hope to be able to meet and discuss further, even maybe conduct, joint research in this field in the future. Thank you for joining us.
Well, thank you. I am excited about this field on all levels. I very, very much appreciate the chance to interact with you. And I hope it leads to a continuing interaction, even if it's not a collaboration, whatever it is. If there's any way I could help you short of sending money, I would be happy to.
I mean, intellectual advice is, nowadays is more precious than actual money, so it's money is, secondary in this matter. Thank you.
So thanks very much. I really appreciate it. I enjoyed it.
You.
Thank you.
Thank you very much.